All right. Objectives for today. You should be able to define thermal energy. So you should be able to tell me what it is. Okay, and then at the end of class, you should be able to distinguish between thermal energy, temperature, and heat. So the fact that we are distinguishing between them means they're likely not the same thing, right? So be paying attention for what they are. And also be listening for those agree or disagree statements. We'll discuss them as we get to them in the notes. Okay. All right, we're going to start off with thermal energy. Okay. You are used to by now the idea that all objects have energy because we've learned about that. Objects have kinetic energy when they're moving, and they have potential energy when they have the potential to change. Okay? Well, like objects, the particles that make up those objects also have energy. And they have kinetic energy when they are in motion. So the faster those particles are going to move, the more kinetic energy they are going to have. And particles move at different speeds depending on what state of matter they are in. So particles that are in solids are bonded very tightly together, so they can't be moving around. So all they can do is vibrate. So they do not move very much. Therefore, they have low kinetic energy. Particles that are in gases have a little more freedom to move around. They move more quickly and they have a higher kinetic energy. And then your liquids would fall somewhere in the middle. Particles also have potential energy. The potential energy of a particle is based on their position relative to each other. So remember that particles have attractive forces between them, and therefore the distance between those particles determines how much potential they have to move. If they are like solids and the particles are closely packed together, there's less potential for those particles to undergo a change, and so their potential energy is going to be low. If they are like gases and moving around more and having more distance between them, then the potential for those attractive forces to change them is greater, and therefore they have greater potential energy. When we learned about objects, we said that when you add up the total potential and kinetic energy for objects in a system, you wind up with what we call mechanical energy. There's a similar concept for particles, except when you add all the potential and kinetic energy of a group of particles, we call that their thermal energy. So your thermal energy of a bucket of water would be if you took the kinetic energy and the potential energy of all the particles in that bucket, added them together, that would be your thermal energy for that bucket of water. So go ahead and turn to a person sitting near you, a partner or a small group, and tell them, how would you solve for the thermal energy of a bowling ball? So who would like to share? How do we find the thermal energy of our bowling ball? Potential plus kinetic energy. So you'd find the potential energy of all of the particles in the bowling ball and add it to the kinetic energy of all the particles in the bowling ball. And that would give you your thermal energy. Now, we understand what thermal energy is, but in order to answer our first agree-disagree question, where we are comparing thermal energy and temperature, we have to understand what temperature is to know if they are the same thing, right? So, temperature is a measure of a particle's kinetic energy. So, you're measuring the kinetic energy of that particle. Okay. And if you're measuring the temperature of an object, you're measuring the kinetic energy of all the particles in that object. It's not likely, however, that all of those particles will be moving at the same speed. Just like it's not likely for all of you to move at the same speed if I sent you out on the track to run a mile. But if I took the whole freshman class and I gave you a time for the freshman class to run the mile, what time am I probably giving you?
9 minutes.
How would I get to that number?
Take an average.
Take an average, okay? I would give you an average speed by taking all of your times together, averaging them, and giving you your average speed. That is what we are doing with temperature. Temperature is a measure of average kinetic energy. So you're taking the average energy, kinetic energy, available in the particles of that object. Because thermal energy measures potential and kinetic, it's not going to be the same as temperature. Okay? For example, you could have a puddle of water that is in the process of melting. So it was frozen over and now it is melting. If you took the temperature of the water in that puddle and the temperature of the ice in that puddle, they would likely be very similar. However, their thermal energy would not be the same because ice is a solid, and so it's going to have less potential energy, and as a result, it will have less total thermal energy than the water, which would have more potential. So they're not the same because temperature only measures kinetic, and thermal is the sum of kinetic and potential. Now, it would be pretty easy for me to measure how quickly you're moving around the track, right? I just use a stopwatch to time you. However, it's more difficult to measure the kinetic energy of something because you're trying to measure energy, and especially to measure the kinetic energy of something small enough that being able to observe it will be difficult. So we had to come up with ways to measure temperature and measure the average kinetic energy of these particles. And the tools we use to do that are called thermometers. There are a couple different kinds. The most common kind that you have probably run into is a bulb thermometer. A bulb thermometer is usually made of glass and it contains a liquid like mercury or an alcohol solution. And what happens, which you observed in your lab yesterday, is that as you heat the thermometer, okay, the particles in the substance you're measuring the temperature of transfer some of their energy to that thermometer, and they cause those particles to gain kinetic energy and move faster, and as a result they spread out, the liquid expands, and the line of liquid moves up the tube, and that's how you know that a temperature is increasing. When kinetic energy increases, particles move faster, and as a result they move farther apart from each other. The opposite is true when temperature decreases. Particles lose energy, they move slower, and as a result they are able to move more closely together. The liquid contracts and it moves down the tube. Okay. Another thermometer that you may have run into is if you have electric thermometers at home, like the ones you put under your tongue that have a digital readout on them. What they are doing is they are measuring the change in the resistance of an electrical circuit. So when temperatures change, the difficulty of passing electricity through a circuit changes, and based on how that changes, the thermometer is able to give you a readout of your temperature. All right. The last important piece to know about temperature has to do with temperature scales. Temperature scales are just ways of measuring the temperature, and the difference between scales is they're all measured in degrees, but how much a temperature changes, how much energy changes between those degrees is different for each scale. The one you are probably most familiar with is Fahrenheit, because that's the one we use here in the United States. Okay? On the Fahrenheit scale, water freezes at 32 degrees, and it boils at 212 degrees. What's nice about this is that each degree on the Fahrenheit scale doesn't amount to a huge change in energy. So as a result, we can feel more temperatures. It's easier to tell the difference between 60 degrees and 80 degrees. Okay? Because there's more variability there for us. The Celsius scale, which is part of the metric system, water freezes at 0 degrees and it boils at 100 degrees. What's nice about this is that it's very standardized and it's easy to tell it just moves a little more linearly. It's easier to remember, oh, water freezes at 0 and boils at 100. These numbers are easier to stick in your brain. The problems we run into with the Celsius scale is that the difference between degrees is much greater, so there's a much bigger jump. So a number like, 40 degrees Celsius could be room temperature. So it's harder to feel the difference in those temperatures and have them correlate nicely to numbers for you. The last scale that we're going to talk about is the Kelvin scale. This one was created for scientific purposes, and because of that, you will see it largely used for scientific purposes. On the Kelvin scale, water freezes at 273 degrees, and it boils at 373 degrees. These sound like crazy numbers, and that's because the Kelvin scale is based off of absolute zero. 0 degrees Kelvin is what we call absolute zero, which is the point at which particles have zero kinetic energy and are no longer moving. The problem with absolute zero is that absolute zero is a theoretical number. We have been unable to measure any particles at absolute zero because in order to measure the kinetic energy of a particle, you need to touch that particle with something. And if you touch that particle with something, it's going to transfer energy to it. And then it's no longer going to be at absolute zero. There's no way to measure the temperature of something without interacting with it, and if we interact with it, we change its temperature from absolute zero. So we haven't been able to actually measure this in a lab because of those issues. So it's a theoretical number. It could exist out there, but we wouldn't have a way of measuring it, and that's why you'll see this largely used in scientific stuff. In science, we try to standardize the scale we use to help us eliminate confusion when communicating numbers. We try to all use usually Celsius. However, if you're going to use another scale, it just becomes very important that you label it. Because if you're talking about 10 degrees, if you're on the Fahrenheit scale, that's below freezing. And if you're on the Celsius scale, it's above freezing. So it's important to know which scale you're using. All right, the last thing we need to talk about today is heat. Heat is a measure of the movement of energy. Specifically, heat is going to be the movement of energy from a warmer object to a cooler object. Heat always moves from high to low. So, what that means is that our second agree-disagree statement is accurate. Heat is the movement of energy from a high temperature object to a low temperature object. If you touch an object and that object feels warm to you, what you are feeling is energy leaving that object and entering your hand. On the flip side, if you touch an object and it feels cooler than you, then energy is leaving your hand and entering that object. And if you happen to touch an object and it doesn't feel warm or cold, then that object is likely at the same temperature you are, and since there's no higher temperature for energy to move from to a lower temperature, then energy doesn't move. It's at an equilibrium there, and so you will feel like it's the same temperature as you. Heat and thermal energy are not the same thing. Thermal energy is your total energy available. Heat is measuring moving energy, energy moving from one substance to another. All right, that covers our last objective. So we are going to go ahead and end notes there.